much thinking we're going to be done. I'm not sure. We'll see how it kind of plays out, but this week with class meetings, so that after Easter we might have a few more scheduled class meetings, but it'll be kind of organized or announced, is what I'm thinking. So that is all right. All right, so we left off with problems with this. We had the back of the chapter. Did you guys have any questions on the back of the chapter problems that were due? We got through what, number 3, I think, in class.
On number 4.
Number 4.
They asked us to run a t-test on that.
Okay.
All I did was take the standard error.
Yeah. Yeah, that's probably, yeah, just having you do it by hand kind of. So, and that was in the T-stat area of the one app on how you can calculate it by hand. Yeah. Okay. Good. Anything else? Okay, so week 5, we start the second half. And so the forecasting is kind of the nature of this one, which is similar to the idea of time series, but not necessarily the same. So when we think of demand estimation, we're trying to think of making a prediction. We've estimated a demand curve, and we think that the regression runs like this, so that if I decrease price by this amount, I will sell this many more units. Right? So that was our demand estimation chapter, what we spent time on. So now we're going to be trying to forecast, especially using time. So if we have data that looks like this over time, and we do an estimation and we have a trend line that looks like this up to today, then our boss wants to know, well, what's going to happen tomorrow, right? Are we going to be here, here, or here tomorrow? That's the magic question always, right? So how are we going to be able to make predictions and forecasting what we're going to be tomorrow? So now we're going to use some slightly different techniques, but still kind of in the theme of regression and stuff, but and try to, using this previous data, if we were to graph a line through here or something, you know, does it go like this or does it go like this? If I grab the data from back here, it might have a little bit different look. So what's the appropriate amount of data to grab onto to forecast ahead? So if we think about forecasting for our company next month, well, 2 years ago might not be appropriate data to use at all, right? So what's the relevant data to be using as we move forward? Okay, so that's a quick and dirty intro. You can read through this stuff on your own. And let's go ahead and grab onto the growth models. Just start right in with that one. App number 13. There it is. Okay, so again, let's kind of look at what we've got going. It's got the Merlot, and then we've got seasonality terms, some other junk here is what he's done. So again, we're going to kind of have some raw data, and then we're going to be modifying that data for reasons to try to maybe do some predictions. So estimating growth rates using regression. As noted in the discussion of calculating growth rates using the beginning and ending values on pages 139 to 40, this may lead to problems, especially if the beginning or ending values are not typical. A more balanced method of calculating growth rates is to use regression to estimate the growth rate. A constant growth rate model takes this form. So there is the standard form. Now this looks kind of familiar. Who's got their eyeball on that and sees something similar to what we've done? Yeah, the present value formula, right? So 1 plus r raised to the t power. So this is our present value formula that we've all come to love and know. Let's do the future value is equal to present value I raised to the n power. So there you go. That's what we're doing here. That's how you measure growth rate. So it's just compound growth, the normal. But when we look at it mathematically, not always necessarily put it into the context of money. It could be the growth rate of mold in a house that has mold growth or something, right? If that follows some sort of exponential formula, we could be measuring the amount of mold that you're going to have tomorrow, given that today you have this much mold, and mold grows at 3% over the next time periods. What is the amount of mold in your house going to look like? Okay, so yt is the value of the y in time period t, b is the initial value of y, and r is the growth rate. So notice that b is the initial value of y. So these are really the same variable, right? So this is this variable. So they could have used probably some y t0 or something like that, but they often chose to use b here. This equation cannot be estimated using regression analysis without transforming the dependent variable. Why? Why can it not be used using regression analysis in the form that it is? It's not linear. Yeah, that's all there is to it. So when we use regression, it has to be in y equals a plus bx form. And then now we've learned that you can have bx1 plus b2x2 blah, blah, blah. But it has to be in kind of slope-intercept form. This function is not. And so now we're back to doing the log transformation, similar to what we did for the constant elasticity of demand stuff. So this equation can be turned into a linear function by taking the logs. Natural log versus log sheet shows the natural logs are the preferable way in this instance. So natural log, and then that is the transformation by doing the mathematical approach of taking the logs. The t, the exponent, comes down to being a shift parameter, and then you've got the log of the thing in the brackets. So just like what we did with the other growth models. This means that all we need to do is run a univariate regression where the dependent variable is the log of y and the independent variable is t. The growth rate r is obtained from the estimated regression coefficients as r equals ed minus 1. This example uses the one series from the demand seasonality app, Merlot, which we'll spend some more time on this week as well. This series presented in A2 through A53. A2 through A53 is our first column of data, so they just grabbed onto the Merlot data here. And exhibits strong seasonality. So to focus the attention on the growth model, this series has been de-seasonalized using techniques presented in the seasonality and seasonal indices. The log, natural log versus log sheet compares two regression models and uses those numbers. So here, first of all, how does this seasonality and de-seasonalized, how does that strike you? What do we mean by seasons? Let's start fresh here, make sure we're all on the same page.
Like take away when the log rates are not in the season.
Yeah. So we think about snow removal. Is that a seasonal job? Yeah, we need snow. There's not too much snow to move in July. So that's a seasonal concept. So the word seasonal comes from, naturally the 4 seasons, but it could be monthly or something else going different, so that at different times, when we look at the time series, the main thing we're coming back to is this. that there might be certain areas where the peak, it's always higher than another time. And so if we're trying to predict long-term trends, we can get rid of that. So what this graph is showing is a technique that we'll spend some time on, where you can see the seasons right here, right? So the peak is the Merlot unit sales. We have a spike, we have a spike, we have a spike, we have a spike. And so you can kind of flatten that out to kind of get a long-term trend. So if you were trying to predict where are my Merlot sales going to be, 2 years from now, it would be more appropriate to think about this red line and moving up than it would be maybe one of the blue ones. Is that data given to you? Yeah, it's part of this other example that we'll show. So let's see. So here's we're going to click this button here in a second. I wanted to show the D-season. This is, I guess these are just basically showing the same thing. This is the log versus natural log. But all right, so let's click this button. See if this brings me to where I want it to go. Oh gosh. I usually do this from the textbook, so I thought I'd give this a try. Oh, and he does have the natural log versus log tab here for us. That was just kind of cranking out the model like we've done before, using the logs versus natural logs. So back to this data, and then he's got this little quick button up here. You can click back to the main document if you want. So this is where he shoved extra stuff. Notice how the columns are at BC, BD. So basically, he just put all of that other stuff we were looking at is at the other end, and then he gives these little quick buttons to get back and forth to. Okay, so here is the time periods, 1 through 52, and then he's got some ones and zeros put in here for these, and let's see if he's as descriptive here as he is in the. Yeah, here we go. Okay. All right, I'll give this a try. You might end up turning on the document camera and going from your textbook. But so here's the 13 steps produced to deseasonalize the series. So a time counter was created in column BA. So what does he mean by a time counter in BA? That's that first column over here. What is a time counter? Period. Yeah, it's arbitrary periods. So basically a time counter, like we know that, let's say this was 2011, 2012, 2013, 2014, 2015, and so on to 2016. A time counter might just say, well, this is time 1, 2, 3, 4, right? So from the Excel standpoint, we're just going to put a number that's really arbitrary, whether this could have been January, February, March, April, May, June, and I still would have put 1, 2, 3, 4, right? So it's just counting the number of time periods associated with each data. All right, so that's BA. So you actually create that, like if you guys in your paper would run into something like this with your data set, you literally go the 1, 2, 3. Who remembers the shortcut here? If you do 1, 2, 3, let's say all of this was gone. Delete. Anybody remember how you do that? Like how would do I have to sit here and type 4, 5, 6, drag it down? So I think you can do it with just 3. And then it just goes. So that's how you create the time clicker in terms of what he's asking to do for this problem. Okay, good. We're polishing up our Excel skills. There we go. Back to normal. Okay. A set of seasonal dummy variables were created in columns B1 through N. So what's a dummy variable?
0, 1, okay.
Some other number. So yes or no, male or female, right? is things you can use as 0-1 code for the computer. So those are our dummy variables. And there are 13 periods for this. So if it's 13 periods, we're working our way through 52 weeks. So they've got it into how many, let's get back to time periods here. 13 periods. Data. Why is it 13, do you think? So we've got 52 time periods. That's running this way with time. But then we've got these groupings. What's the 13? What's magical about 13? Why wasn't it 12? Why wasn't it 5? Why wasn't it 26? Prime number. How many weeks in a year? 52. So if it was every 2 weeks,
It must be every 4 weeks.
so yeah, every 2 weeks would be divided by 2 equals 26. Divide that by 2 equals 13. So what are we measuring here? Every 4 weeks, right? So what's the problem with if we use monthly, January, February, March, like I was doing here? Some weeks have 5. Yeah, you guys learned that. Well, maybe you have learned that already with your paycheck. Sometimes you get an extra paycheck in a month, right? So that's what's going on. Some of the weeks it doesn't fall perfectly. So really, that's a function of your data. You guys wouldn't have known this. I mean, I wanted to reason through the week thing, but this particular, a lot of companies will use the 13-week thing so that it's very consistent as you go through the year on what week you're on. Oh, I'm on week 13, I'm on week 6, rather than using the words February or March, because of, it makes the books a little easier if you're going in 4-week increments and it follows the calendar year. So not terribly unusual to do something like that during or for business type data. All right, so we create those. So there are 13 periods in this instance. These are easily labeled, type first, second, third, highlight both, and it'll go to the 13th, so you can use that kind of fill thing to get the numbers. Note columns BM and BN were originally switched, and BO and BN, BO is in BN. Okay, I don't remember exactly what that means. You guys know what that means? Oh yeah, there's a gap. Okay. Oh yeah, that was with the 12 and 13. Okay. So let's see what he says there. Columns BM and BN were originally switched, and the BO is in BN. And I think that's the last one. First. All right, we'll learn later. Anybody know what's going on there? I can't remember. This isn't the way it worked in the books, but I don't know if he's saying it was originally switched, like that's the way the data came to us, or not. He might be saying that, but I'm not sure. Yeah. Okay, we'll find out. So natural log was created in column BQ. So the natural log is using Excel equals ln of that cell, right? And then filling down. So you're creating log data, transforming the raw data into log data. A preliminary regression was run using the log Merlot as the dependent variable. Time and the first 12 seasonal dummies were included. The first 3 columns of that regression are in BW1 through BY30. So BW1 through B30, all in here.
So what did they use as the variables for the dummy variable? What's the next one?
So yes, you got the dummies and time. And the dependent variable was log of Merlot. So that's what's kind of weird. Remember, this picture here we're taking log of Merlot. So that's the dependent, the y variable if we were entering this into Excel. And then we're measuring it over our time counter. And then what the dummy variables are going to do, well, you guys tell me. So what are the dummy variables doing, do you think, here when we have it run with the dummies? So here's your full, this is kind of your full regression, right? There's time, there's our x variable, and then we have the dummies. Oh, I know what the dummies. Just not. Are they significant? Let's start there. Why? Above 2. So we go back to our t-stat. So here's our t-stat. And so what does that mean when a coefficient is significant? What's that rating? Okay, it'll greatly affect it, and it has meaning to it, right? That it's different from 0. So when we did it with pizza up here, and we found that the price of pizza was significant in the quantity of pizza sold, then we're just saying, oh, price is important. So this is saying time is important. Time at a specific period of time, like the 8th period or whatever. So we have these variables that are changing, and time seems to be important, meaning this data shows some seasonality to it. Right? So it is saying that, oh, August looks like this, and it's important that, I mean, if you remember, Excel is dumb. It's not as smart as you guys, for real. It's only as good as you are. So what it's doing is it's saying, oh, the number 3 is an important variable in determining Merlot. Well, that sounds dumb. Why would the number 3 be important in Merlot sales, right? Well, the reason is because at number 3, all the data points tend to be in a certain location, so 3 is important. And when we go to 7 down here, they're down here, so 7 is important too, right? So it's, again, the seasonality. There's ups and downs. The data is moving over time. Okay, questions or comments there? This is where your intuition is good to kind of keep in check when you get into this time series stuff, because it seems pretty weird that we're using time as an independent variable, right? But that's the difference between time series and cross-section data. Okay. Okay, the rest of the regression was started to save space. So the seasonal dummy variables were examined to find a large positive coefficient. The largest positive seasonal dummy was removed, and the regression was rerun. In this instance, the 12th was moved to VO, and VN was moved to VM. See the blue. So that was this part here. And let me see if any of you guys have figured out what's going on with removing one of those time periods. This was covered in the dummy chapter, the dummy variable content that we did in the previous apps. We never even, well, it was in the material. We talked about it that one day in class, and there's a whole Excel app that talks about dummy variables. So you should go back and review that, because that one's kind of important. I'm not saying you need the answer to this right away, but remember, if there was 3 in that dummy app thing, if there was 3 places, how many dummy variables do you need? 2. Why? Well, not necessarily that only 2 are relevant. No, it's not so much that. What if we go to the yes, no? You guys can pull up that app if you want. So if we had yes, no, or something as an answer, and let's do a gender bender one here. Let's say that gender turned out to be significant. And so you gave a 1 to females. Female equals 1 and male equals 0. Both male and females are important and significant in terms of the thing. So we ran the regression and we found out that the female 1, where we had the 1, was significant. What did it do to what did it say about the data? Look back on that Excel app. I don't remember which one it was. Oh wait, I can't remember. Is this the one that has the dummy variable? 3A. 3A. So what did it do? I pretty much have the answer in front of you now.
What about the raising or lowering intercept?
Yeah, that's because it's 1, 0. All you're really doing is affecting the intercept. And so, which one of these is, I can't, what was this, residential? Yeah. Which line is residential and which one's non-residential? The top one or the bottom one? Which one's residential? Residential bottom one. How do you know that? Because we got the -3, right? So this is residential, this is non-residential. Both of them are important variables, if you will. But how do we get the difference? We only need one argument in the regression to pick up the 2 things we're trying to do, right? So it's kind of like conceptually, you're like, oh, is it residential or non-residential? Is it male or female? If you run a regression without it, you get this, let's say. So let's say you don't use a dummy variable and you get this, right? And now you do run a variable and then it's going to shift, it's going to make a distinction between the 2 by just adding 1 of the 2 elements. So you thought gender was important. It's kind of like 2 variables, male or female, but your one without it is the other one because of the 1, 0 nature of how you're doing it. Does that make sense? So back to our Merlot data. You're talking about the Merlot one, or? Yeah. Yeah, well, and I just wanted to point out that that's why we got rid of one of these. So we're using dummy variables. There's 13 of them, but you can only run a regression on the 1, right? Or you have to on 12 of them for the same reason male female. The one without is the one with the additional. So you're just dropping it off. Okay, so that's just a little nuance with the dummy variables, and now this is applied to
The one that you get the 12th one and on.
because of the 13th period being the start of the first. So you actually have it continuous that way. All right, so the missing period was added back by moving CG to CA30 and CA29. So let's look at what he means by that. CA29 and CG29. Right here. And that was with the 12th. And then the 13th. So this is a little bit with making sure that the estimate lines up with the right one. So they moved that data down because they switched them with the results. It's actually the 13th. Okay, so this missing period is added back. This is the green space. Calculate peak indices by exponentiating the seasonal dummy variables CH19 through CH31. CH19. They are CH19 through CH31. So if you double click that, you're picking up the coefficient and getting the percent change that it was. So that's undoing what we did before to get it back to figuring out where the peaks are with this, depending on the magnitude of the coefficient. I'm gonna continue to work through this, and then I want to show you the one in the book, because I think the one in the book is a little more intuitive. But this one uses the regression. All right, so obtain the sum peak of the indices by auto summing in CH32, and then create an average. So if we auto sum down here, what is the number for 12? Is 100. So how many of you remember the price level? Back to macro class. We created the price level. What was the formula for the price level? That was the rate of inflation. But how did we actually create the actual index number? I'll give you a hint. It was related to gross domestic product, GDP. It was a simple ratio. So formula time, Capstone experience, the price level. See if Eddie remembers what the formula for the price level, like CPI. It was the ratio of two variables. Hint, it was GDP, GDP, GDP. And now there's just two simple letters missing. R and N. Which one goes up top? R. Okay. N. Yeah, the 50-50 shot. So nominal divided by real GDP gave you the price index. Now, what was the price level in the base year? So I'm bringing this memory back to you so that now you see what we're doing here with this data, right? All we're doing is we're picking a base year basically, and we're saying, how does this number compare to the base year? How does this number compare to the base year, right? And so we've kind of done a base year thing by looking at the averages. So now once we do that, so we do the auto sum, which is the sum of all those numbers. And then we're at our next step here. Create an average indices by multiplying the peak number by the number of periods per year and dividing them by the sum of the peak indices in CI through 21, which is this one. So there's the formula. This number, the peak, times 13, which was the number of time periods, divided by the average. So we're looking at the percentage change over time. And then that gives us our average change over the 13 time periods. All right, you're probably getting about lost by now. It's not super easy. I think the one in the book is a little more intuitive. We'll get to that in a sec. Let's work through this. Calculate the peak indices by exponentiating the seasonal dummy variables. In C13, obtain the peak. Yes, move down. Number 10. Check your work by auto-summing the averages. Copy and paste special. What's the paste special again? Okay, so it takes the formula. Paste special gives you the value. That's a real important function to use. In BR through B14, see the highlighted yellow cells. BR through B17. We followed what, so this is the average now, the average index number. We're taking off the small one here. Copy and paste the values from BR check your work by auto summing the average. So you're creating this average index number, and then putting it back into the yellow cells, because this is a formula. So we're just putting that back over to here. So see, this one is 99. I know my print's kind of small, but that's 0.9, this is 99.3. So this was the formula, we're just cutting it back into raw data. And the reason we're doing that is so that we can then use that data again to do another regression. Okay, so type equals BR2 to that, so that subsequent year indices can be obtained. Oh, so then you can fill down. I'm going to gloss over that to BR15. Yeah. So then once you do this, you can then put it down and flow it down if whatever equals that BR. Create the seasonalized data series by dividing the series by the average index value. In this instance, type that. And in BS2, and double click to fill the column, the results is the one is the same provided in column C. All right, so return back to the main document, and that's how they did that. Let me show you the textbook version of this.
How do you know when you're supposed to use logs or not? You're just trying to get something from a non-linear to linear, then you use logs.
Yeah, the natural log had with the elasticities, that the coefficients are the elasticity, so that was the advantage. So pretty much just use natural logs, but I think just to be complete, he shows both. And there we go. Okay, let's start you off here. So if you guys have yours, we're going to do a little round robin reading. I'm going to have you read through. We're going to read through quite a bit of this. So Dakota, you can start us out, then we'll go to Luke, and then Brady, and then Eddie, and then JC and Liz. Okay. 143. I think I can't go quite that. So the fact that
time series analysis does not take into consideration positive factors does not mean that an analysis using this method should not consider additional information about changes in underlying forces. Any analysis using
any analyst. So and the reason I correct you is we're talking about a person, an analyst, rather than an analysis, right? It's a person who's doing the work.
Any analyst.
Analyst.
Oh my gosh. Any analyst using this naive method of prediction should try to fine tune the conclusions based on information that can alter results.
All right, next reader.
When data are collected over a number of periods in the past, they usually exhibit 4 different characteristics. The first one?
Yeah, go ahead with the first one.
Trend. This is the direction of movement of the data over a relatively long period of time, either upward or downward.
All right, next reader. Cyclical.
Cyclical functions. These are
Deviations.
deviations from the trend due to general economic conditions. For instance, if one were to observe data from GDP over time, the long-run upward trend would be evident. Also, evident in the series would be movement around the trend as the economy rises more quickly or less quickly.
Seasonal fluctuations, a pattern that repeats annually is characteristic because toy sales tend to rise greatly before Christmas. Fashions have spring and fall seasons. In the soft drink industry, the expectation is for higher sales in the corn period, like in June through September. less time series, which data are collected more frequently than monthly reported, and exhibit seasonal variations.
Irregular quantities from the normal report, especially when it may just represent more necessary, like randomly and does not be. That's a consideration to refer to the following information.
All right. So we've got the dependent variable being a function of trend, cyclical, seasonal, and irregular, right? So we've got those things kind of in our minds, conceptually trying to understand what's going on and to make better predictions. So the trend, when we did our GDP, I got GDP up here, right? That was kind of the one you've seen plenty of times. So over time, if we look at real GDP, it goes up and down. We have our trend line, which is kind of the average trend line going up. And then you've got this thing going up and or down, depending on potentially these different factors. Okay, so the specific form of this equation could be additive. Other forms also exist. The specification most commonly used is the multiplicative form. So the dependent variable is these things multiplied. Thus, the changes in the actual value of y are determined by 4 factors. The task of the analyst is to decompose the time series of y into its 4 components. We can now return to Frank Robinson's problem of forecasting citronade sales, which was an example he was doing before, not only for the entire year of 2013, but for each quarter. The entire procedure is summarized in Table 5.5, an alternative method of obtaining seasonal indices using regression analysis to examine the seasonality and seasonal indices Excel at. That's what we did. All right, so here is basically what the author was doing in a little bit different way, and we'll come back to this example. He was using the Merlot data, but it's kind of similar. So here is the quarters of the year. So we had 44 quarters. And then this was the actual amount of citronade sales in each quarter as it went through. And you can see that in third quarter, boom, there's a bump. Sixth, there's a bump, right? So you kind of have these moves jumping around. So now come back and let's see, who's our next reader? Go ahead and read that plus column 1. I guess do the next one too. Okay, so where we're going with this is we're going to do a moving average. What was that? I think I mentioned it once, but I don't think you had to deal with it. What is your average change every single time? How is it changing or why is it changing? Every quarter. Now, think about what we're trying to do is we're trying to, it's like the seasons of the year, right? January or fall, spring, winter, all that. So we've got but here it's identified by quarters. So each quarter is 3 months of the year. And so what we're going to do is we're saying, oh, what's the average of that? So over these 4 quarters this year, the average was 973. So what's this one calculated on? 5. The 5? No.
2 to 5.
2 to 5. So it's what we're doing is we're going to move the 4 that we're calculating. So the next data point is going to be these. So you're keeping it at a year, and these, and these, and these. And so then you have a moving average is actually every quarter, but it's those 4 quarters are included, and the average is moving as we move through time, right? So it's a 4-quarter moving average
Is the moving average basically the same thing as the trend line? Would that be the same thing? Same thing, the same concept?
Yes, it's the same concept. So what we're doing is we're by taking the you're going to see it in the data that we do, but since you asked, if we take a moving average, we're going to smooth out the humps and then go. We're basically doing something like this, right? Because we're smoothing it out. We're taking all four and compressing them. There still might be some ups and downs, so it's not a straight line. Is my point. It's not the trend line, but it's smoothing it out. Okay. Any other questions or comments so far? Okay. So column 3. Go ahead and whoever our next reader is.
The first step in the DC deciding process is to calculate a quarterly average for the first year. The result is 973, so this number is placed next to quarter 3 in this column. Next number is changed by moving down one quarter. First quarter is dropped, fifth quarter is added, and the average of quarters 2, 3, 4, and 5 is calculated to be 989. This number is placed next to quarter 4. Same procedure is involved in the rest of the quarters. Because of the average, data for the first 2 quarters and the last quarter are lost. First moving average is placed next to the third quarter. It will also be placed next to the second quarter. Actually, the average of the 4 quarters belongs between the second and the third quarters. This computation is made in column 4.
Okay, so there. Basically, so that last comment is that, hey, if we were really doing the moving average for these 4 numbers, doesn't it belong at 2.5? Right? Technically, if you're kind of thinking the way averages work, if we're putting equal weight into each quarter, then 973 really belongs right here at 2.5. Okay, next reader. I can't remember where we're at.
An average of 2 adjacent numbers in column 3 is calculated and replaced in the third quarter. The 973 column 3 should have appeared between quarters 2 and 3, and 989.3 should have been between quarters 3 and 4. The average of these two, 981.1, is correctly placed at quarter 3. All centered moving averages are placed in column 4. With this procedure, the next to last number is now lost.
Okay, so now we're averaging out those 2 averages. Oops. All right, autofocus. Wonderful thing. So now this number is correctly here on the third quarter by that last maneuver. By averaging the 2, we end up getting it back in line. So we are being pretty precise at the placement in quarter 3. We want it to be the correct average. So that's the centered moving average. Now places 981 there. Is everybody cool on that? All right. That was column 4 that we just did. Now column 5.
We now obtain the seasonal factors. They are ratios obtained by dividing the actual numbers in column 2 by the centered moving averages of column 4. Observing the numbers in column 5, it can be seen that every 4th quarter, starting with quarter 3, has a factor greater than 1. These quarters represent the summer months when soda consumption is at its peak. It's also can also be seen that the data for the second calendar quarters are rather close to 1, where the quarters representing fall and winter are generally below 0.
Okay, so now when we do number 5, the ratio is the actual number divided by the centered moving average. So now we're comparing how does the actual number compare to the centered moving average. Why is that important? Oops, that's really hard to tell how it's important when I have my fat fingers over, not even on the screen. So back to my question here. We're on column 5. and we're saying the ratio of the actual number compared to the centered moving average. What is that telling you?
The closer it is to 1,000, the closer to 2 numbers.
Okay, so the closer to, when you say 1,000, what do you mean?
So like in the center moving average, like look at number 4, 999,
Okay,
you have 875 and 876. And you have like the 981, the one above it, you have 1236, 1260.
so what is it showing you the relationship of between the two numbers, like in terms of the interpretation of this one is 0.88 and this one is 1.26? What's significant about that? Dakota?
The difference of the time of the year.
Yeah, it's picking up the seasonality part of this, right? And so if we look at my picture that I drew over there with the green, I'm trying to make this.
That line is from 3 to 7,
There.
so high.
Kind of works. What's it in relationship to my picture here?
It's 1.26 of the trend line.
Yeah, over the, not the trend line, but the moving average, right? So all, think about it mathematically, all we've done is we've taken the centered moving average, which is at time period, this one, whatever this is, time period 9. The centered moving average is that, and the actual data is this. So what we're seeing is that in time period 9, the actual is higher than the CMA, but we get it at a quick glance because we've done this ratio, right? If it's over 1, is it above it or below it? It's above it. And if it's below 1, is it above it or below it? Below it. That's all we're doing. So here in time period 10, again, I'm not relating it to there, the centered moving average is here, the actual is here. And so it shows up as a 0.88. It's just a ratio. Okay. So let's see here. Next round. Okay. I think we're on 6. Next reader.
Column 6, to obtain a quarterly seasonal index, we must average ratios between by quarter and this is done in table 5.6. The quarterly patterns are quite obvious.
Go ahead and finish it off.
There appears to be a minor downward trend compared to quarter data. This is discussed later.
Oh, did you lose me here? I wanted you to do all of 6.
I guess I have more.
Oh, really?
I have, yeah, there's a line right here.
What? Oh, you must have a new edition. Okay. Okay.
4 averages.
So you read all of 6?
I'm about to read the second.
Okay. Go for it.
There's a line in between
Oh,
those 2 quarters.
okay.
Those 2
Okay.
The 4 averages should add 2 4. They do not because of rounding. A minor adjustment must now be made. The results are then transferred to column 6.
Okay. So seasonal index, we must average the ratios obtained by column 5. So here was our ratio of the ups and downs, 1.26 and 1.88. And now we're going to do the averages of those. So we're really smoothing again the data, right? We're basically doing another modification to the ups and downs.
How do you get 6? You get the average of 2.
Yes.
Where is
This is, so obtain the quarterly seasonal index. We must average the ratios obtained by quarter in column 5. So by quarter. So this is done table 6. The quarterly patterns are quite obvious. The 4 averages should add to 4, but they do not. So when we look at 6, oops, sorry. So they're saying the 4 averages should average out to be close to 4.
How did they get the average score of 1 and 2?
I think you're taking this data and placing it there, the first 4. So this is off down here. I don't know, Eddie, does yours say? I guess we can just do it. Maybe that's why they added that extra language. What was that extra language that you had in yours, Eddie?
There appears to be an iron downward trend. Discuss later.
Oh, okay. So go ahead and take the average of those four. Take those four and find the average of those four. Now it should be around 1.
Yeah, I got one.
Yeah. One, pretty much.
All right, let's see if it comes together after we do it. I can't remember, you guys, honestly, off the top of my head. I know I've worked with this before, but
When they
it
added
fell out.
up, it looked 4.
Huh?
When you added those 4, I think you might be 4.
It did.
Yeah,
Okay.
it might be a 4 and a little over.
But I think your question is a good one. We're averaging the ratios obtained by quarter in column 5. Oh, wait. Ah, yeah. Never mind. I knew I was missing something. They reference table 5.6. That's on the next page. So here we go. This one tells you how they did it. So first quarter, second quarter, third quarter, fourth quarter. So with each one, for each year, they've got the time. So first quarter, 8.9, 8.72. Yeah, because it starts with the third quarter of 2002. That's your 1.26. So they're picking up right here, 1.26, 0.87. And then they've got it laid out here, 1.26, 0.87, 0.89. So it's running in this direction. So then here's your average and adjusted average down at the bottom, 0.89. So look at what happens here, 0.88, 0.89, 991, 1.2, and then it's repeating again. See that? Is everybody seeing that? It repeats all the way down. So that's your baseline. So then we'll use that to create the index. That's like your base year in a sense. We've got it kind of narrowed down to that factor by averaging out the quarters. So this is the adjusted average. So this is the numbers that we're getting replicated right here. And this is what he said about the rounding. It's close to 4, but not quite. All right, good to move on? Good enough? All right, number 7. Who's the next reader?
When the actual data of column 2 are divided by the sequence factors of column 6, the decentralized series of numbers in column 7 is obtained. Or if the actual on the decentralized data be positive figure 5.6, the latter series that should be expected is much smoother than the former. Okay,
so then we've got the deseasonalized data. We're applying that factor to calculate it. So when the actual data of column 2 are divided by the seasonal factors, then we get the deseasonalized. So we're adjusting the 842 and dividing it by the seasonal factor. That has deseasonalized that. So this is a low period and now it's that. Notice that the actual in quarter number 3 is high, but taking out the season brought it down, right? So we deseasonalized the data through kind of manipulating it this way. Okay, so the trend line. So this is the last parts here are getting the trend, the cycle, and the irregular together. So next reader. All right, stop there. So we've got a very significant number, right? So is that above 2? Yeah, it's very above 2. And how about the goodness of fit? 99.6, so 99% of the variation is explained by the time part once we've used the deseasonalized numbers. Okay, next reader.
Exponential quadratic equations also have very high R squares, but their t is typically lower, and square terms are actually not statistically significant.
Okay, so then we jump down to column 8. Using this equation, we arrived at the trend numbers in column 8. So here's the what Excel spit out to us, right? Slope-intercept form, we're back to the intercept and the slope, and now we're going to shove in time period 1, time period 2. And then that number is all we have for column 8. Using time as the explanatory variable, that is our trend. So we're just allowing it to crank out a number, and that's our trend. Column 8, then, by dividing the data in column 7 by those in column 8, we eliminate the trend from the deseasonalized series in terms of the fraction used previously. So they're getting rid of the trend part because we have that multiplicative function, and we're dividing by t. All we're left with is those two, C and R. And here, let me jump to this picture real quick. So actual data, and then the deseasonalized data. So almost a straight line by sucking out those variations through manipulating this. So thus, only the cycle and random elements remain in column 9, which is in percentage form. And then lastly, next reader. Okay, so this next section that we'll do, just because this could be a nice way to put a bow tie on this. Before we leave the section on projections, one other naive method should be mentioned. So naive methods sound stupid, sounds simple. It's at the very beginning of this. Let's see here. Good forecasting. Right here. All right. So forecasting techniques can be categorized in many ways. We use the following 6 categories: expert opinion, opinion polls, survey of spending plans, economic indicators, projections, econometric models. So next reader here, start off with this paragraph.
As we see in the following pages, some of the methods can be classified as quantitative, qualitative, others as quantitative. Qualitative forecasting based on judgments of individuals or groups. Results of qualitative forecasting may be in numerical form, but generally are not based on a series of historical data. Quantitative forecasting, in contrast, generally uses significant amounts of prior data as a basis for prediction. Quantitative techniques can be naive or causal. Naive
Causal. Causal. I just want to make sure, because casual, let's be casual about this. You know, we don't want to wear a bow tie or anything. So causal meaning cause and effect, right? So we're trying to get a causal chain, so which turns out to be pretty difficult. But again, important correction here, so that's why I had to jump in. So naive or causal?
Naive forecasting projects past data into the future without explaining future trends. Casual explanatory.
Causal. I understand, it's okay.
Attempts to explain the functional relationship between the variables to be estimated, the dependent variable and the variable or variables that account for the changes in the dependent variable.
Okay, so let's just stop there. So naive forecasting projects past data into the future without explaining the future trends. So we are going to, we come up with some fancy techniques with moving averages, but we haven't talked about what the underlying thing is with citronate sales. We haven't put the price of beer in there. Like maybe beer is an important variable in determining citronate sales. You see what I mean? So once we start doing what we did in the other forecast, where we actually start putting some variables, then we're getting more causal. But the naive forecasting, naive is not to say that it's bad. It could actually be an appropriate way to do some forecasting. But you're simply taking historic data and moving a time period up. And so the way we deseasonalized, again, that might be appropriate to say where we're going to be at in a longer time frame since we've deseasonalized. But your best guess of what is GDP going to be next month might be, well, what is it this month? Well, I think my best guess would be whatever it was last month, because it's just too hard to guess any other number. I'd just be speculating. There's equal probability if we did a little probability distribution. Well, that's really ugly. Whatever. I was just trying to say equal chance of being high or low. Then your best guess is probably what was it last month, right? And that's a naive forecasting method, just using previous data. Okay, last thing, then we'll be done. We've got a couple minutes left here. Go ahead and next reader. Okay, we'll leave it there because we really, explained what moving average was from there. So that gives you guys a good taste of time series data. We'll call it a